Welcome to another video tutorial session on finite element procedure for solving one-dimensional problem. In today's video, we are going to solve this problem using both hand calculation and the finite element procedure. This problem shown here cannot be solved using the elimination method. It can only be solved using the penalty approach, the penalty method. Even though we are using the penalty method, we need to understand a concept called multipoint constraint model approach to solve this problem. The multipoint constraint equation is added to the penalty approach to solve this particular problem. I'm going to explain the multipoint constraint model to you in this video tutorial. In this problem that we're going to solve today, we have two flexible material, the part between node 1 and node 3 and the part between node 2 and node 4, and they are both in tension under a load which is attached to this rigid beam at node 5. The magnitude of the node P is 30 times 10 raised to power 3. We're told that this beam is rigid, so it does not deform. So the effect of the load is just to rotate the beam element about this hinge support. We see we have an hinge support. This hinge support tells us that this is not fixed. There's actually rotation at the support. So we are asked to calculate the tension in the two parts that support the rigid beam, part 1 and part 2. The first part, we are told that is made of steel material. The Young modulus is 200 gigapascal. The length of the part, that is the distance between node 1 and node 3, is 4.5 meters. And the second part is made of aluminium material. The Young modulus is 70 GPa. The length of the part between node 2 and node 4 is 3 meters, and the cross-sectional area of the part is 900 mm². So to solve this problem again using the penalty method, we need to understand the concept called the multipoint constraint model. I'm going to explain this model, the multipoint constraint model, in my next slide. So let's move to the next slide. Okay, I'm actually not going to explain the multipoint constraint model now. First, I'll solve the problem using hand calculation. After the hand calculation explanation, I will explain the multipoint constraint model. So what you see on my screen is an AutoCAD sketch of the 1D structural problem. And on my right, this part of the drawing, we see that when the load is applied at node 5, when the 30 kilonewton load is applied at node 5, we assume that the beam rotates. There's a small rotation about node A. If we assume there is a small rotation about node A, the rotation will cause the finite element 1, that the part 1, which we call finite element 1, to stretch by an amount called Q2. Let me zoom so you see it better. So when the beam rotates, the finite element 1 stretches by an amount called which I term Q2, because I define my node at that point as 2. So I prefer to define the deformation at node 2 to be Q2. At node 4, we also have a deformation Q4, and at node 5 we have a deformation which I term Q5. So our question is actually to determine the stress in the finite element 1 and finite element 2. We can also determine the reaction at node 1 and node 3. I numbered my model in this format: node 1, node 2, node 1, node 2, node 3, node 4, and node 5. The important part of this problem is actually the flexible part. I'm not numbering node A because it's not an important part that affects the model. I number node 5 because there is a point load, there is a boundary condition that affects the finite element. That's why I numbered node 5. And if you should notice, I only we only have two finite elements labeled in the drawing: finite element 1 and finite element 2. The part between 2 and 4 is rigid, so I didn't number that part. You don't need to number that part. Actually, this explanation I'm giving is actually for the finite element, is the finite element explanation, is for the finite element solution. For manual calculation, we don't actually need this explanation now. So I've explained that a small rotation about root A will cause Q2, Q4, and Q5 deformation at node 2, node 4, and node 5. So if we use two equilibrium equations, the first equilibrium equation, summation of moment at A equals to 0. If we sum moment at A equals to 0, because we have a pin support at node 1 and node 3, that means we'll have a reaction force at node 1 and node 3, and the reaction force will point upward. Why is it pointing upward? Because we know that finite element 1 and finite element 2 is in tension. So for it to be in tension, the forces the reaction force has to point upward. So if we sum moment about A, we get 2R1 plus 5R3 equals to 180. Let's term this equation 1. Another equation which we can call the compatibility equation is that, let me use my razor to clean all this, is that we can relate the deformation of at node 2 and node 4 together using a compatibility equation. Like, if you should notice, we have some triangles here, which let me see if I can sketch it out. Triangle A2, this small triangle, and this triangle 2, 4. So these two triangles are similar. Pardon my drawing. These two triangles are similar triangles. So if we say for the first triangle, we can say distance between node A and node 2. We know that as 2000 mm. Yeah, this distance from this node to this node, which from this node to this node, we know the distance as 2000 mm. So we say 2000 using similar triangle, 2000 over Q2, that is this deformation, is equals to distance from node A to node 4. It's equals to 5000, which is 2000 plus 3000. That is 5000 mm divided by the deformation at node 4. So this is a compatibility. This is the second equation, which is a compatibility equation. So we can solve this and we get this relation: 5Q2 equals to 2Q4. So this, let's term it equation 2. We're going to use these two equations to solve our problem. So I'll move to the next slide now. We can write the equation of the deformation at 2. That is the extension of the bar at 2 using Hooke's law formula. Extension equals to PL over EA. For finite element 1, the P is the reaction force at the support R1. So we say R1 times the length of finite element 1, which I call LS, length of steel, the Young modulus of steel, which I call ES, the area of the steel, which I call AS. So this is PL over EA. So if we should write this equation, Q2 is the extension. So Q2 equals to this equation. So if we should write this out, we get 1.875 times 10 minus 5 R1. Let's term this equation 3. We do the same thing for Q4, the extension at node 4 of the finite element 2. The force is the reaction force at the support, which is R3. So R3 times the length of the finite element, which is 3000 mm, 3 meter. The length of steel is 4.5 meters, it's written here. So this is where we have, that's why we have 4500 mm here. The unit I'm using is Newton per millimeter. So this 4.5 meter, I converted it to millimeter. So the length, as I was saying, the length of the second finite element is 3 meters. That is 3000 mm. The Young modulus is 70 times 10 to the power 3 Newton per millimeter square. The cross-sectional area is 900 mm square. So we solve this, we get this relation. Q4 equals to 4.762 times 10 minus 5 R3. This equation, which we got in the previous slide, this equation, which we got in the previous slide, our compatibility equation, we can substitute Q3, Q4 in the in equation 2, which is this equation. So if we should substitute it, we will get this relation, this force relation. R3 equals to 0.984375 R1. So we now have two force equation. This equation here and our equation 1, which is also written here. Our equation 1 in the previous slide. This equation 1, 2R1 plus 5R3 equals to 180, which is also written here, 2R1 plus 5R3 equals to 180. So if we substitute the value of R3 in this equation, we can get our R1, our reaction at node 1 to be 26.0045147 kilonewton. And the reaction at R3, if we should substitute R1 back to this equation, we get R3 equals to 25.598191 kilonewton. So these are our two reactions. So now that we have gotten our reaction, we can calculate the stresses in both finite elements, force over area. For the first finite element, the area force is the reaction 1. So reaction 1 divided by the area of the steel, which I term A1. So the force divided by area of the steel. The area of the steel is 1200 mm square. So that's why I divide by 1200 mm square here. So we should compute that, you will get 21.67 MPa. We do the same thing for the second finite element. The internal stress in the second finite element. That is the reaction at, that is the area force in finite element 2 is reaction 3, R3. So R3 divided by A2, that is the area of the aluminium, the cross-sectional area of the aluminium. So if we should compute that, we get 28.44 MPa. So these are the two internal stress in our finite element problem. To compute Q2 and Q4 is very simple. We can use the formula PL divided by EA, where the P where the P is represented by, where the P for deformation are true, that is deformation of finite element of finite element 1, where the P is R1. So R1 times L divided by EA. So if you substitute R1, which is 26.00 times 10 to the power 3 Newton, you have to convert it to Newton. Remember, this is in kilonewton. Multiplied by the length, which is 4,500, the length of the finite element, divided by E, which is 200 gigapascal, divided by 1,200, the cross-sectional area of the steel. So we get our deformation at node 2, Q2, to be 0.487585 mm. This is the exact solution. We're going to compare these results with our finite element solution in this lesson at the end of the video. Q4, that is the elongation of finite element 2. We can also compute it, where our P is R3. That is easier for us in finite element 2. So we should substitute, we get this value, 1.218962 millimeter. So these are the values for the reaction, for the internal stress, and the deformation in both finite elements using hand calculation method. In my next slide, I will explain the penalty method to solve this problem. But we are going to apply a concept called the multi-point constraint approach. I've already recommended a textbook in one of my previous videos on introduction to finite element procedure. So I strongly advise you study the book maybe to understand this multi-point constraint model. I will try to explain a bit of it in this lesson now. The multi-point constraint model is applied to it's mostly applied to two particular problems. We apply it to inclined roller support problem and rigid connection. When we say rigid connection, we mean, like in this our question, this our one-dimensional problem actually has 5 boundary conditions. There's a boundary condition at node 1. There's a boundary condition at node 2 that moves. There's a boundary condition at node 3 that does not move. There's a boundary condition at node 4 that moves by Q4. And there's also a boundary condition at node 5 that moves. So we use the multi-point constraint model to define problems where we have more than one displacement boundary condition. When we have more than, here we have 3 displacement boundary conditions. So we need to apply this multi-point constraint model. This inclined roller, I'm going to have, we use it to solve problem where we have inclined roller support. There is a particular problem which I've solved before and which I'm going to solve in my future lesson. It's actually a two-dimensional, a plane source problem with inclined roller support. Let me see if I can find the MATLAB script where I solve the problem, so I can show you what I'm talking about. This is what I'm talking about. This is a plane source problem. You can see we have at node 3 a roller support which is inclined an inclined roller support. So we need to, in this type of problem, we need to apply the multi-point constraint model to solve this problem. So this is another problem where we can apply the multi-point constraint model. I'll go back to my PowerPoint now. For the multi-point constraint model explanation, I'm not going to actually explain the theory a governing theory and that supports the model. I'm going to just explain what you need to know about the model to solve this problem. What is most important about this multi-point constraint model is this equation here. Beta 1 QP1 plus beta 2 QP2 equals to beta 0. This is actually what it means. Henceforth, let's refer to this equation. Beta 1 Q1 plus beta 2 Q2 equals to beta naught. Beta 1, beta 2, beta 0 are coefficients, which we will find when we define this equation. Q1 is our displacement support without load, while Q2 is the displacement support, is the displacement boundary condition with load. And using the multi-point constraint model, we always need to relate one boundary condition without any load with another boundary condition with load. Like in this problem, let me zoom. In this problem, Q2 is a boundary condition that with displacement without load defined. Q4 is node 4 is a boundary condition without any load defined. Node 5 is a boundary condition with load applied. So for this question, we need to relate node 2 and node 5 together, and also relate node 4 and node 5 together. So what the summary of it is that you have to relate two nodes together, a node without boundary condition, without load applied, and a node with displacement with load applied. The node without the boundary condition without load applied is the Q1, is the Q1, while the node with the boundary condition with load applied is the Q2. Like for this question is the Q2. So if we should write an equation connecting Q2 and Q5 together, we'll get an equation of this form. And when we get an equation of this form, you pick the coefficient of Q1, it will be beta 1. Let's say you have 5 Q1 here, that means beta 1 will be 5. Let's say you have minus 3 here, that means beta 2 will be minus 3. Let's say you have 0, this equals to 0, that means beta 0 will be 0. So we need to determine, when you are writing this equation, the next thing to do is to determine the coefficient. That is beta 1, beta 2, beta 0. And when you have determined it, you substitute it in this matrix. And this matrix, we need to add this matrix to our global stiffness matrix. Remember how we assemble our global stiffness matrix, we add up all the local stiffness matrix. We also need to add this matrix to the global stiffness matrix at node 1 and node 2, along the row and along the column. For the first, so that means we also need to modify the global stiffness matrix with this matrix. With this matrix, we need to add this to the global stiffness matrix. For the first vector, we need to add this to the first vector too. C multiplied by this vector, and the vector is defined as beta naught multiplied by beta 1, beta naught multiplied by beta 2. So we need to add this at node 1 and node 2 in the first vector. I'm going to explain this in the MATLAB code, and even in this slide, in my next, even in this PowerPoint, in my next slide. So you modify. In addition to modifying the boundary condition without displacement, like adding field to the diagonals, adding a large stiffness to the diagonal. We also need to add this to modify the boundary condition with displacement defined. This is for the global stiffness matrix. This is the modification for the first vector. So you should note. So the important formula here are this formula, this formula, this formula, and this formula. And when you have modified when you are done modifying your global stiffness matrix and your Gauss vector, you can determine the displacement quantity by inverting the modified global stiffness matrix, the inverse of it, multiplied by the first vector that was modified. So you get your Q matrix from that. And you can also determine reaction at all supports in your finite element model with this equation. This is a very popular equation in the finite element procedure. We use this formula in many instances. We even use it in a source problem. We use it in beam problem. We use it in frame problem. So this formula is also it's also applicable for one-dimensional problem. So I'm going to explain this, like how we generate this modified matrix for the K and for the first vector in my next slide. So I told you that we need to relate a boundary condition with displacement support without load with a boundary condition with displacement support with load. So 2 and 5, we need to relate node 2 and node 5 together. And how do we relate it together? Assuming a small rotation about node A, the rotation has to be small for us to for our assumption to be correct. Assuming a small rotation, and we know that the beam the beam is rigid. That means the beam will not stretch. It's not flexible. So we can, if we assume a small rotation, this is a triangle. This is a triangle, and this is another triangle from A to 5. So relating these two triangles together, this is our first multi-point constraint equation. We also do for 4, 5, but now we're doing for 2, 5. We also do for node 4 and node 5. But I'm doing for node 2 and node 5 now. So relating these two similar triangles together, we get 2000 mm. That is the length from node A to node 2 divided by the vertical displacement Q2 equals to 6000. That is the distance between node A to node 5. Sorry. That is the distance. Sorry. So that is the distance between 6000 mm is the distance between node A and node 5. 2000 plus 3000 plus 1000, 6000 divided by Q5. So if we should solve this, you get this equation: 3Q2 minus Q5 equals to 0. So from here you can define your beta 1, beta 2, and beta 0. Beta 1 is 3, we see. No, Q2 is, now I told you Q1 is Q1. This Q2 is representing Q1 in our base in our formula. In this formula, Q2 is our boundary condition without load. So this 3 is our beta 1. Here is -1. The coefficient of Q5 is Q5 is our boundary condition with load applied. So this is our like node 2, this Q5. So and the beta 2 is -1. The beta 0 is given as 0. So using this equation, so we get beta 1, beta 2, beta 0. So if we should substitute these beta values in this matrix equation, we get 9 minus 3 minus 3, 1. Square root beta 1 square is 3 squared. That's why we got 9 here. So we get C, a large stiffness, multiplied by this matrix. But the node numbering, you should note it, the node numbering is the node you consider, node 2 and node 5. The boundary condition we consider boundary condition at node 2 and node 5. So 2, 5 along the row and 2, 5 along the column. So we are going to add this matrix at this position in our global stiffness matrix. C multiplied by this matrix, we are going to add this at 2, 5 in the row and column respectively in our global stiffness matrix. For the first vector, because our B0 is 0, so B0 times B1 is 0, B0 times B2 is also 0. So that means we don't need to, if there's a value here, that means we have to also add this value, this vector, to our first vector at position 2 and 5. But because it's 0, we don't need to do any modification to the first vector. So we only need to modify our global stiffness matrix. So this is for 2 and 5. We also need to do for 4 and 5. That's another multi-point constraint. So we do the same thing for 2 and 5. Considering this triangle A4 and the triangle from A to 5. There are two similar triangles. So if you consider that triangle, you can write this equation. The distance between node A and node 4 is 5,000 mm, 2,000 mm plus 3,000 mm. 5,000 mm divided by Q4, that is the displacement at node 4. 6,000 mm, that is the distance between node A and node 5, which is 6,000, divided by Q5. So we get this equation. In the same way, we can define our Q4 will represent our Q1, Q5 will represent our Q2. Q5 is the boundary condition with load applied. The other Q is the boundary condition without any load applied. So we define, from this we can define beta 1, beta 2, and beta 0. And we can form this equation and also form this equation. But for this, we add this matrix at position 4 and 5 in the global stiffness matrix. Because at that node 4 and 5, 4 and 5, 4 and 5. So that means we need to add these two to modify our global stiffness matrix. So if this is the only difference, we have been solving different one-dimensional problems using the penalty approach, but we need to incorporate this in the penalty approach method. So this is what, if we have done this, the rest is the same with what we have done before. I'm going to move to the MATLAB working environment now to show you a practical explanation of this multi-point constraint model. So now I'm on the MATLAB working environment. So this is our question. In the question, we've already defined our model with two finite elements. But however, I'm not using this number. I am using this numbering. I'm not using the numbering in the question. I'm using this numbering. So you should note this. The node at this support is my node 1. The node at this support is my node 2. The node at this support is my node 3. The node at this support is my node 4. And the node at this support is my node 5. Okay, let me copy this image so that I can paste it in my MATLAB working environment. So we don't need to switch. So, so we see it. This is our finite element model. It has 2 finite elements and 3 multi-point constraints, Q2, Q4, Q5. Node 1, node 2, node 3, node 4, node 5. So it means our stiffness matrix will be a 5 by 5 matrix. So now what we need to do, we need to define our global stiffness matrix for finite element 1 and finite element 2. So to do that, you need to define the geometric and the material property of both finite elements. In the question, we're told that the area of the first finite element is 1,200. The Young modular is 200 kilopascal. The length is 4.5 meters, which is what I define here as L1, A1, E1. This is stored in the MATLAB memory when you run the program. When I click here and run the program. So once I do this, I can immediately calculate my global stiffness matrix, which I term K1, using the stiffness matrix for one-dimensional linear element. We know this formula now. I don't need to display it here. So I calculate my local stiffness matrix for K1. So this K1 is computed to be equals to this 5.33 times 10 to the power 4. Same thing is done for element 2. In the question, we're told that the cross-section area is 900 mm, the Young modulus is 100 kilopascal, the length is 3 meters. I define this parameter here, L2, A2, E2. If you should run, it is calculated and the value are stored in the MATLAB memory. So once you have computed this, you can also compute your local stiffness matrix for element 2. So it's evaluated to be equals to this. Now our K1 and K2 has been defined and calculated. K1, K2 is the local stiffness matrix of our finite element 1 and 2 respectively. So once we have defined this local stiffness matrix, we can now define our global stiffness matrix for our entire global stiffness matrix. So as we always do, the first thing we do, we need to define a base matrix, which is a 0 matrix. And because our problem has 5 nodes, our base matrix will be a 5 by 5 matrix. So that's why I'm using this 0 function, MATLAB function, inbuilt function, to create a 0 5 by 5 matrix. So I should enter 5 as input variable. This 0 5 by 5 matrix is stored in a variable called K. This K is representing my global stiffness matrix. So now we have created a 0 5 by 5 matrix, which we assign to a variable called K. Now we need to assemble all the local stiffness matrix into the global stiffness matrix. The K1 will be added at position 1 and 2. Why is it added at position 1 and 2 of the global stiffness matrix? Because it is located at that point at node 1 and it's located between node 1 and node 2. So that's why I'm using 1 column 2, 1 column 2 plus K1. So we see here that the K has been added at position 1 and 2 of the global stiffness matrix. We do the same thing for K2, but K2 will be added at position 3 and 4 of the global stiffness matrix because finite element 2 is located between node 3 and 4. So you can see I use 3 column 4 comma 3 column 4 to assemble the matrix, and I added K2. If you should see, this is the K2 matrix which is added in the position 3 and 4 of the global stiffness matrix. Now we need to apply the penalty approach. And the penalty approach, where we don't have displacement, what do we do? What do we normally do? We add a large stiffness, which is defined as which I normally term C. So the first thing I did, I redefined this K matrix to mod K. Mod K equals to K. So mod K is now representing my modified stiffness matrix. So we need to define our last stiffness, which we will add to the global stiffness matrix. And the last stiffness is given as the maximum value in this global stiffness matrix multiplied by 10,000. This line of code multiplied by 10,000. So if I can use the max function to query or to evaluate the maximum value in the matrix. The maximum value is actually 5.33 times 10 to the power 4. So this function extracts that value, and I multiply that value by 10,000. So we get our C to be calculated as 5.33 times 10 to the power 8. This C value, we need to add it to 2 node points. We need to add it at node 1 and node 3. Why are we adding it at this node? Because we have 0 displacement at that support. For all support degree of freedom, we add a large stiffness. For all support degree of freedom with 0 displacement, we add a large stiffness called C. So at node 1, along the diagonal 1, 1, I will add C, and also at 3, 3 at the diagonal, I'm going to add C to the global stiffness matrix. So you can see the MATLAB code that adds C to position 1, 1. So C is added. When I run this code and I run, C is added to this position. You can see the other values now are very, very insignificant. C is added to this position. Same thing is done for 3, 3. C is also added in the 3, 3 position of the matrix using this code. You can see the value here. Now, after we have applied our last stiffness at all 0 support degree of freedom, we need to now apply the multipoint constraint model to the. We need to apply the multipoint constraint matrix to this modified stiffness matrix. So in my PowerPoint, for the multipoint constraint equation that affect Q2 and Q5, the multipoint constraint equation that affect Q2 and Q5 is given by this equation, 3Q2 minus Q5 equals to 0. So it means our beta 1 equals to 3, our beta 2 equals to minus 1, and our beta 0 equals to 0. So that's why, so our first multipoint constraint equation, I define B1 as my beta 1, B2 as my beta 2, 3 and minus 1. I don't need to define beta 0 because it's 0. And it does not affect my first vector. So I only define beta 1 and beta 2. And I then defined the matrix which I showed you. I defined this matrix on MATLAB by running this code. So C multiplied by the matrix beta 1 square beta 1 times beta 2 semicolon beta 1 beta 2 beta 2 square. So B1, B2 is substituted in all these positions, and this is formed. This is our first multi-strain constraint matrix. So we need to add this, as I told you, at where? At position 2 and 5, because that is the node we are considering, at position 2 and 5 of the global stiffness matrix. So this matrix will be added at 2 and 5. You should note that. I also for our second multi-point constraint equation, our beta 1 is 6, our beta 2 is minus 5. Let me quickly show you on the PowerPoint. We see this is our second multi-strain equation. Beta 1 is 6, beta 2 is minus 5. So we can, so that's why this is defined like this. So this, what I'm actually doing, I'm rewriting the value of this. So I'm changing beta 1 to 6. It was actually 3 before, but now I'm changing it to 6. And I'm changing it to minus 5. But it's not going to affect this equation because I wrote this code after this MATLAB code. So this change is not going to affect this, because MATLAB runs from top to down. So B1 is redefined as 6, B2 is redefined as minus 5, and is substituted in a matrix I call C mod 2. This is my second multi-point constraint matrix. If I should run this, this is formed. This is formed. So now I have two multi-strain constraint matrices, which I want to add to my global stiffness matrix. The second multi-point constraint matrix will be added at what point? It's going to be added at node 4 and node 5, because that is the node we are considering, node 4 and node 5. So this will be applied again. The first matrix will be applied at node 2 and node 5. This C mod 1, while this C mod 2 will be applied at node 4 and node 5. So you can see this MATLAB code doing exactly that. I have 2 and 5 here, 2 and 5, comma 2 and 5, adding C mod 1. So if I should run this code, I get this. So this gets added. You can see it gets added at this position, this position, this position, and this position. At this 4 position. At for the second multi-point constraint matrix, we add it at 4 and 5, as I have said earlier. 4 and 5. So we add C mod 2 at 4 and 5. So it gets added to the modified matrix at these 4 points. So this is all the modification we need to do to the stiffness matrix. So now this is the modified stiffness matrix, considering all boundary conditions. Now we need to define our modified global displacement matrix. So we need to define our modified global displacement matrix Q. To do that, we have already defined our stiffness matrix, but we have not defined our force vector. The only force acting on the model is 30 kilonewton at node 5. 30 kilonewton force at node 5. At other node 1, 2, 3, 4, the forces are 0. So I create a 5 by 1 matrix, 5 rows, 1 column, 5 by 1 vector, 0, 0, 0, 0, 10,000 Newton. So this is created. When I run the code, I turn my force vector F. So I can calculate my displacement vector by inverting mod k and multiplying by f. You can write it in this format, you get your answer, or you write it in my usual format, inverse mod k multiplied by f. So let me run. So you get your q to be equals to this. Remember, I'm not modifying my first vector. Why? Because the b naught is 0, so I don't need to modify my my first vector from the multi-point constraint side. I don't need to do that. And also because at node 1 and node 3, the displacement is 0, the gap is 0, a equals to 0. I don't also need to modify position 1 and 3 of it because there is no displacement at that node. So we run it and we get this. At 1, we get a very small value. It's supposed to give us 0, but give us a very small value. At node 2, we get 0.4876 mm. This is actually what we got in our hand calculation. I'm going to, I'll refer to it now. At node 3, the displacement is actually supposed to be 0. Yes, because we have a 0 support degree of freedom at node 3. At node 4, the displacement is at 1.2190. At node 5, the displacement is 1.4628. So let's check the displacement at node 2 in our hand calculation. We are getting 0.4876 here. In my hand calculation at Q2 is 0.4875, 0.4876. Very identical, exactly the same with hand calculation. Q4 is 1.2189. Let's check what Q4 is. 1.2189, 1.2190. Almost the same. In our hand calculation, we didn't calculate Q5, but the finite element procedure is giving us the value of Q5 to be equals to 1.4628 mm. Now we have defined the displacement vector. We can now also define the stress in each finite element using the stress equation. Let me just copy it so you remember. Maybe you have forgotten the formula now. I have not forgotten, but I'm sure many of you guys have forgotten the formula. So this is the formula we're using. So this is our stress equation. So if we substitute our E divided by L multiplied by these matrices, it gives us our stress equation. So for the sigma 1 is representing the stress in my first finite element. So E1, which is 200 kilopascal, I've defined it before. L1, which is 4.5 meters, 4,500 mm, and multiplied by this matrix, which is this minus 1 and 1, multiplied by this matrix. Element 1 is found between node 1 and node 2. So that's why this is defined as 1, 2. So I extract the experiment quantity at node 1 and 2 from the Q matrix, which we just calculated, this matrix. So I'm extracting the displacement quantity at 1 and 2. And we get our stress. When I write this code and I run it, we get our stress in element 1 to be 21.6693. We do the same thing for the second element. the same explanation, but finite element 2 is located between node 3 and 4. That's why this is defined as 3, 4. We also run this, we get 28.4430 megapascal. So let's compare the stress calculation with our manual calculation. The first one is 21.6693. 21.6693. This is giving us 21.67, almost the same. 6693. This is 670. Sigma 2 is giving us 28.442. What does 28.442 megapascal? MATLAB gives us 28.443 megapascal, which is very identical to the hand calculation. So now we have determined the internal stress in each finite element 2. We can also determine the reaction at all the nodes, node 1, node 2, node 3, node 4, node 5, using this equation which I showed you in my PowerPoint. I told you this is a very popular equation in finite element procedure. The reaction, which is defined as R, equals to the K multiplied by Q minus F. This K is the unmodified global stiffness matrix. Unmodified. The matrix where you've not added any large stiffness or multipoint constraint stiffness. That's what this K is. And thank God I still have such. You can see this is the K matrix where I only added K1 and K2. We see it. I have it stored in my MATLAB memory. Q is the displacement calculated at the 5 node. This matrix here, Q. So I multiply K by Q minus F. F is my force vector, or the unmodified force vector, but the F we didn't modify it at all. So F is representing our unmodified force vector, and the only force value in the model is at node 5, 30,000 Newton. So we should run this code. We get our reaction at node 1, node 2, node 3, node 4, node 5. Node 1 is minus 2.60. Remember, if you look at my force vector, I'm taking force pointing downward as positive plus 30,000 Newton. That means this at R1 that is negative, the force is pointing upward. So which agrees with the assumption that finite element 1 is in tension. You can see that this value should be correct, minus 2.6003. I think I calculated this in my hand calculation. I'm going to check it. So at node 1 we have minus 2.6003. At node 3 we have minus 2.5599. Let's check these two values. Now calculation. R1 is 26 kilonewton, which is the same thing. Minus 2.6 times 10 raised to power 4 minus 26.003 times 10 raised to power 3 Newton minus 26.003 kilonewton. At node 3, we have minus 25.559 kilonewton. In my hand calculation, I have 25.598 kilonewton. And see, the result is very identical with the hand calculation. So this is how we solve this type of problem using the penalty approach while applying multi-point constraint model to this solution. You can see this solution, we calculated deformation at all the nodes, node 1, node 2, node 3, node 4, node 5. We calculated the stress in our two finite elements, finite element 1 and 2, and we also calculated reaction at all the nodes. Also, this value at node position 2 2.6003 is the reaction at node 2 pointing downward. At node 4, 2.5599 times 10 to the power 4 is the reaction at node 4. You should note that. So this gives us reaction at our 5 nodes, which is very accurate. You see, I will try and validate these reaction values in my finite element model on ANSYS. In my next video, I'm going to solve this same problem using the ANSYS program. So we have come to the end of this tutorial session. Stay tuned for my next video, where I will solve this same problem using the ANSYS program. Thank you so much for taking your time to watch my video on YouTube.